Hello there. This is a session by Biofield Strawhecker around improving enterprise automation agility by leveraging REST. There's a little bit of meeting to before we start. The meeting is being recorded, and everybody will remain on mute throughout the presentation. But if you've got any questions, please just put them in the chat, and if there's a suitable time, I'll just interject and Phil, I'll ask you a question if that's okay. Otherwise, we can always wait until the end when I'll unmute everybody. Otherwise, it's over to you, Phil, to make a start, please.
Okay, if we're ready, then I can go ahead and start. Is that what you're asking?
Yes, please. I think there's a few over joining, but yes, please, yeah.
Okay, will do. All right. Hello, everyone. Like Stephen said, my name is Phil Strawhecker, and I'm a member of the Ops MBS development team here at Broadcom. And in this presentation, my goal is to show you why you should consider using REST-enabled services to help you in your enterprise automation strategy. Now, before I show you the benefits of using REST APIs, I'd like to spend a little time describing the REST protocol itself. REST, of course, stands for Representational State Transfer, and it's more of an architectural style of communication than an actual standard or protocol. You know, the data elements known as resources are passed between a REST client and a REST server without either side needing to know implementation details such as required platforms or programming languages. Now, this resource data is transmitted in a stateless manner, basically meaning that each request stands on its own and doesn't rely on previous or future requests in order to be processed correctly. Now, while not explicitly stated in the original REST definition, most REST servers today operate as web services using HTTP and TCP/IP as the transport mechanism. Now, if a web service conforms to the REST architectural style, this web service can be called a REST API. Now, in today's presentation, I'll describe one such API and how REST clients can use this API in combination with other REST API endpoints to accomplish a couple of different automation scenarios. Now, in the modern business landscape, companies are constantly trying to improve their enterprise automation strategies. So, what are some of the limiting factors to be able to re-architect these policies and procedures? Now, I'm sure this comes as no surprise, but each business area has its own team of personnel that have, over time, developed their own solutions to problems faced by the specific business area. While they may have a detailed understanding of the requirements of their own area, they may not understand how their data and processes impact other areas of the business. Now, in addition, their selected tool set, either homegrown or off the shelf, may not be designed to easily share data with other unrelated applications. The tool set and procedures used by one team may not be the best choice to automate other areas of the business. These other areas may require specialized hardware, or those automation teams may choose to use different set of platforms and tools to match their own skill set. And due to budgetary and other concerns, at least some of the processing power used to automate business processes may be part of a cloud computing cluster. Now, the systems used today to automate a certain area may need to change in the future due to either changes in the business process, monetary considerations such as, of course, cost-cutting measures, or changes to the business itself reacting to its competitors. Now, these changes can either be temporary or permanent, which require a certain level of flexibility in whichever automation approach is selected. Excuse me. One of the biggest challenges in the evolving discipline of enterprise automation is dealing with the need for consolidation and the sharing of status between previously isolated business processes. Now, in the past, each business process was managed as its own entity, with each business process team responsible for maintaining their own silo and reporting the status of this silo to upper management on a regular cadence. Now, today, the lines are thinning between distinct business processes as companies are looking for a more holistic view of the entire enterprise. Now, in addition to this holistic view, today's business processes tend to depend upon each other in order to accomplish their individual goals. Now, this shared objective approach requires an increased level of awareness between the individual business systems to ensure that each is made aware of conditions that might impact their combined ability to complete the enterprise-wide objective. Now, most companies have already attempted to automate individual business processes in the past using the tools available at the time. Now, when these companies attempted to include the mainframe into their enterprise automation architecture, the tools used for this integration usually included one or more of the options displayed on this slide. Now, if the solution for your particular business area happened to have an agent that ran on z/OS, this agent would need to be updated at regular intervals and may not provide access to all of the mainframe data required by the remote business process automation engine. The FTP server provided by z/OS provides mechanisms to both remotely copy data to a dataset as well as submit JCL for batch execution. Now, this technique typically only works when talking to a mainframe LPAR, and the ability to route data and commands to the mainframe FTP port may not be allowed from systems that reside in the cloud, for example. Now, if any data is sent back from the mainframe, this data can be hard to parse from the job output log. A remote shell like SSH can also submit JCL to execute a batch job or run a REX program, but this technique does not provide a native ability to transfer status data. Now, it can also be difficult to screen scrape any of these results received over the connection. Now, one solution to the problem of how to share status data among the different types of systems is to use web service APIs based on the REST design philosophy, and again, known as REST APIs. Now, these REST APIs use the Universal Hypertext Transfer Protocol, or HTTP, to transport their data, making the client-server connection easily routable using your existing network infrastructure. The HTTPS variant of this transfer protocol provides a standard mechanism to ensure that any data sent over this connection is secure. The body of the HTTP request, which is the portion of the HTTP request used to actually transport the data, can be in a standardized format such as JSON, which stands for JavaScript Object Notation, or XML, Extensible Markup Language. Or the body can actually consist of unformatted text, just called plain text. The HTTP protocol also defines a standard list of return code ranges to let the client know the result of the initial request. Now, another benefit of using REST APIs is the wide range of client platforms and languages that can be used to communicate with the REST API server. Most, if not all, major platforms available today support the TCP/IP communications protocol and, by extension, the HTTP protocol. Now, these platforms also provide support for various programming languages that can be used to send out HTTP requests to one or more of these REST API servers, since REST API endpoints do not require proprietary software for communication. The REST architectural style of communication requires each request to be stateless, which means that the server must be able to fully process each request from the client without knowing or caring about any previous requests from that client. Now, since each request is considered self-contained, each request can be routed to any server capable of processing the request. Now, this means that the request can be routed to a backup server if the primary server is unavailable or busy, allowing for both fault tolerance and load balancing. Now, while not explicitly part of the REST design, again, most REST APIs also provide a mechanism that allows the definition of a particular API to change without impacting clients written to use these previous definitions. Now, this concept of API versioning allows you to keep the REST API server up to date with the latest features and security patches, while gradually upgrading old client applications to use the new API definition over time. Now, in the next section, we'll discuss how to bring the mainframe in from the cold and let it actually participate in your enterprise automation strategy. Now, one way to allow your mainframe to be notified of events happening throughout your enterprise is to take advantage of a REST API provided by Broadcom's OpsMVS mainframe automation software. Now, this REST API is a collection of secured web service endpoints that provides access to data elements managed by OpsMVS. Now, this REST API is built on top of the Spring Boot architecture, and it's designed to run as a traditional started task using IBM's JSOS batch launcher application. Now, the endpoints made available by this REST API can be called from virtually any platform residing on the same TCP/IP network, including other mainframe applications residing on either the same or remote LPARs, regardless of Sysplex membership. Now, an additional benefit provided by this REST API is the built-in integration with the Zoe API mediation layer, or API-ML for short. The Zoe project is an open source framework for z/OS that seeks to provide a set of tools to allow development and operations teams to interact with the mainframe as if it were any other cloud-based platform. The API-ML component of Zoe provides a gateway to a catalog of registered mainframe-based REST APIs with a single point of access. And registered REST API services can take advantage of features such as consistent access, dynamic discovery, to automatically determine the location and status of available services. And again, these can provide features such as high availability to avoid service outages and scalability by providing load balancing among multiple instances of an API service. Now, as I pointed out on the previous slide, one of the advantages of the OpsMVS REST API is its ability to seamlessly integrate with the Zoe API mediation layer. Now, while the OpsMVS REST API allows you to remotely control mainframe automation data elements, the API-ML allows you to access this OpsMVS REST API using a highly available, consistent interface. The dynamic service discovery capability allows you to programmatically walk through a list of services that are registered with the API-ML to determine if one or more of these services provide the capability you are looking for and whether that service is currently available. The initial service discovery and any future requests to one or more of the registered services are all sent to the URL hosted by the API-ML server. The API-ML acts as a proxy and forwards all these requests to the registered service capable of handling the request. Now, since all service requests are funneled through this API-ML, the amount of required client configuration is reduced since you don't have to define every single service to every single client. So instead of needing to know the connection details required by each REST API server, client applications only need to know the connection details for the API-ML server itself, no matter which registered service is being called. Now, this allows the registered services to change their own connection details without needing to change the configuration information of each client application. Since these client applications only need remote access to the server and port number of the API-ML server, remote connections to the registered services themselves can be blocked, effectively reducing the network attack surface. Now, along with the single point of access, the API-ML can also be used in a high availability environment when used in combination with high availability components such as parallel sysplex and dVIPA, or dynamic virtual IP address. Now, in a high availability mode, the physical API-ML server used to process service requests can change from one request to the next. And again, the ability to process requests on different servers is one of the founding principles of REST, and the API-ML takes advantage of this to ensure maximum availability for all registered services. So if you decide to run the API-ML in an environment without high availability, you can still get some of the features of high availability, such as load balancing and service redundancy. The API-ML allows multiple instances of the same service to register concurrently. So if multiple instances of the same service are currently running, the API-ML will attempt to load balance all requests sent to this service. The API-ML can also operate in redundancy mode, where it will route requests to the first available service instance and consider any other service instance to be a hot backup in case the first service instance becomes unavailable. So for consistency among all of the registered services, the API-ML provides a token-based security mechanism. The API-ML server provides a login API endpoint that can be used to authenticate a user's mainframe credentials. So in response to successfully authenticating a user, the login endpoint returns a security token that can be used in future requests sent to registered services. All registered services will understand and trust the identity of the authenticated user contained within this shared security token, no matter how each service would normally authenticate a user when not interacting with the API-ML. So this login endpoint will either accept a JSON object containing the user credentials to be authenticated, or if no JSON document is included as part of the request, the client certificate used during the TLS encrypted handshake process will be examined to see if it contains the proper user identification information. Now, the primary benefit here is that the returned security token can be used for all future requests, no matter which registered service is contacted. Again, we'll talk a little bit more about this concept in later slides. Now, most of the available REST APIs, including the ones we'll be using as examples later in this presentation, include an endpoint that provides access to a web page that describes all of the available endpoints of that API using the Open API specification format. Now, the Open API specification, which was formerly known as Swagger, is a common API description format used to document REST APIs. Now, in addition to showing a list of all available endpoints, the Open API documentation page shows all of the operations supported for each endpoint, the query and path parameters used by each endpoint, the format of the JSON document used to pass data to the endpoint, the possible HTTP status codes capable of being returned from the endpoint, and the format of the JSON response object sent back from an endpoint, again, if any. To further aid in the creation of REST API client applications, the Swagger project actually contains an open source tool called CodeGen that can generate server stubs and client libraries from any Open API definition. Now, on this slide, you can see the section of the Open API documentation that deals with describing the parameters of an individual endpoint, both query parameters and path parameters. Now, this section also includes the Try It Out button, which allows you to submit a request to the described REST API directly from the Open API specification page without having to write your own client application. Now, this can be extremely helpful if you're trying to write a new client application from scratch that will call the selected endpoint, or you're actually trying to troubleshoot an existing client application. Okay, so now that we have a better understanding of the benefits of using a REST API, let's dive a little deeper and show a couple of examples of how REST APIs can be integrated into your enterprise automation strategy. Specifically, we'll focus on incorporating mainframe REST APIs registered with an instance of the Zoe API ML to get the most benefit from each scenario. Now, in this first scenario, a remote monitoring system has determined that a specific task on a mainframe LPAR needs to stop in response to a detected event. The System State Manager component of OpsMVS manages the task that needs to shut down, so the remote monitoring system will need to request a change in state for this SSM resource that represents the mainframe started task from up to down. Now, this can be accomplished using the OpsMVS REST API in combination with the Zoe API mediation layer. Okay, so again, since we're using the Zoe API ML as the focal point to process all REST API requests, we could take advantage of the single sign-on capability and call the provided logon endpoint to validate the remote system's user credentials. Now, we can specify the user credentials using two different techniques. Again, the first technique is to base64 encode the concatenation of the user ID's ID and password and pass this value to the API ML in the HTTP authorization header. Or the second way is to use the X509 client certificates passed in during the TLS handshake process. Now, once this client certificate is validated, the ID of the user assigned to that certificate will be associated with the login request. Now, either way, the remote system will need to call the login endpoint of the API ML, and once validated, the API ML will return a security token that represents the authenticated user that will be used in all future requests made by our program. Now, as you can see on this slide, we chose to use the authorization header technique for this example. Now, if the encoded user credentials are successfully authenticated, the API-ML will return a response to this post request that contains a cookie called API-ML authentication token. Now, this cookie will then be attached to all future requests in place of any user credentials. Now, in this case, we've also decided to use the Python language in combination with the requests Python package. The requests package contains an API that aids in sending requests to an HTTP-based server and receiving responses from this type of server. The login functions shown on this slide will return a response object generated by the post method of the request API that contains information sent back by the API-ML server, which includes the web cookie containing the authentication token. Now, this cookie will be added to all future calls to this request API, again, in place of the authorization header. Now, this slide shows how the authentication token pulled out of this cookie returned from the login request can be used to issue a request that requires authentication. Now, in this case, we're calling the endpoint that allows us to discover the list of available instances of the OpsMVS REST API. Now, we can discover the available instances of this API by specifying the API ID query parameter with the value of bcm.opsmvs. All services that register themselves with the API-ML must identify which API they support by specifying this API ID during the service registration process. Now, in a real-life application, we would then search this list for the specific instance of OpsMVS we need in order to stop the managed resource. Now, we could do this by looking for a specific service ID or looking for some other defining characteristic of the instance made available when the service registered with the API-ML. But for the purposes of this example, we're just going to go ahead and use the first available instance. So in this case, we're going to issue a GET request against the API-ML services endpoint and return the response object that contains the list of services that have registered with the API-ML using the specified API ID. And again, this will be the list of ops instances that are using the bcm.opsmvs instance ID. Now, again, this slide shows how we can call the endpoint of a service that has registered with the API-ML instead of calling an endpoint that is processed by the API-ML itself. Now, from the caller's point of view, there really is no difference. The parameter op_URL, which is passed into the Python function, actually points to the API-ML server instead of the server hosting the OpsMVS REST API. Now, this op_URL just contains an additional path element that references the OpsMVS REST API service name used during API-ML registration. Now, the remaining path elements correspond to the URI endpoints supported by that particular REST API. Now, the API-ML server will receive this HTTP request. It will parse this URL to determine which registered service should actually be the final destination of this request and forward the request to that server that is hosting the specified service. And again, this is one of the benefits of using the API-ML. Now, if the mainframe LPAR that's hosting the required REST API needs to change, no remote clients will need to know because, again, the remote client only communicates directly with the API-ML. and the API-ML will know to forward the request to a different server due to the change in registration. So in this case, we're going to issue a put request against the URL that represents the SSM resource that is targeted for the status change by the remote monitoring system. Now, this will be accomplished by attaching a JSON document to the body of the put request, stating that the desired state of the identified resource should be set to down. Now, when the System State Manager component of OpsMVS sees this status change request, it will attempt to get the current state of the resource to match the new desired state of the resource by shutting down the associated started task. Now, this slide shows a partial code walkthrough of how a remote client could be written in order to tell OpsMVS to shut down a specific started task in response to an event happening somewhere else in the enterprise. Now, the first step would be to call the login function and have the output from this function parsed to set the value of the auth token variable. Now, this auth token variable will then contain the tokenized value of the user's credentials that will be passed as a cookie on all future calls to the API-ML that require authentication. The next function will use this auth token to call the API-ML services endpoint to retrieve the list of OpsMVS REST API services that have registered with the API-ML. And again, this list will be returned in the JSON format in the body of the response object, and the JSON function is called to return just the body portion of this response. The value of the ops services variable is then set to be this list of services. Now, like I said previously, we will only care about the first service listed for the purposes of this example. Now, each service instance will contain a base URL variable. This base URL points to the portion of the API-ML path dedicated to a particular registered service. Now, in this case, the registered service will be an instance of the OpsMVS REST API. Now, any requests made to URLs underneath this base URL will automatically be forwarded by the API-ML to the associated OpsMVS REST API server. Now, we will pass this base URL along with the auth token and details identifying the specific SSM resource we care about into a get status function. Now, this function will issue a get request to the API-ML using the base URL to target the request to a specific instance of the OpsMVS REST API. Now, OpsMVS will then return the current status of the specified resource using a JSON object in the request's response body. And again, we'll use the JSON function to get the JSON object that is stored in this response body and actually get the value of the SSM details variable to be this object. Now, then we're going to check to see if the requested SSM resource is currently in the up state. Now, if so, we'll go ahead and call the Python function we looked at earlier to set the status of this resource and the status of the associated started task to down. Okay, so in the next scenario, we're going to assume that the portion of a business process running on a non-mainframe system has encountered a situation that affects the entire business process. Now, in this scenario, the remote platform will need a secure and reliable mechanism to notify the mainframe LPAR that is also participating in the same business process of this change in status. Okay, so once the mainframe has received the details about the processing error, the mainframe automation solution will take the appropriate local actions based upon the type of error reported. And again, sending status updates from non-mainframe systems to mainframe systems is not a new problem. Over the years, there have been many different techniques used to handle the transferring of status information between different types of platforms using the non-proprietary mechanisms we discussed earlier. And again, some of the downsides of these techniques include requiring the output to be screen scraped. They might rely on the client being able to open dedicated ports to all of the mainframe LPARs that might be contacted, and they might require each client to keep their list of mainframe LPAR connection details up to date. So if a proprietary solution is used to transport status data between systems, this software may not be able to run on all the systems that require access to this data. Now, by using mainframe REST APIs in combination with an instance of the Zoe API ML, each client that needs to keep a mainframe LPAR informed of changes in the status of a business process can use the same sequence of steps when communicating with the same Zoe API ML server instance. And again, these common steps are calling the Zoe API ML login endpoint. And instead of using FTP or some other transport mechanism to transfer a status document to the mainframe LPAR, we're going to use a built-in service provided by the Zoe API ML itself called the Zoe System Service, or ZSS for short. Now, using this Zoe Service Discovery endpoint, we're going to query for the URL to use when we need to make requests of this ZSS service. And again, since we're going to be using a capability of the OpsMVS REST API to process data contained within this status update document, we're going to use the Zoe Service Discovery endpoint once again to discover the appropriate URL that will process our REST API requests. So now we've discovered the URLs of both of the services that are registered with the Zoe API ML that we plan on using for this task. So we'll start the processes by uploading the status document to the mainframe. And again, this is accomplished by calling the discovered ZSS URL twice. The first call will be to the endpoint that creates a new dataset member, and the second call will be to the endpoint that uploads information to this newly created dataset member. And finally, we're going to then call the discovered URL of the appropriate instance of OpsMVS in order to process the data contained within this newly created dataset member. Now, for this scenario, instead of using Python, I'm going to be using JavaScript code that's actually written for Node.js, and we're going to be using the Fetch API that is available as part of the JavaScript language. Now, I wanted to use a different programming language and a different HTTP-based API to kind of drive home the point that communicating with the REST API can be done with a large set of platforms using a large number of languages. Now, you can use the platform and language that best suits the remainder of your automation tasks while still being able to communicate effectively with the mainframe. So now, as with our previous example, the first step is to authenticate the remote system's user credentials by calling the login endpoint. Now, the asynchronous function shown on this slide will call the login endpoint using the post method and await for the promise to be resolved when a response is actually sent back from the server. Now, just like in our Python example, the response object will also contain a cookie with the user authentication token. But unlike the Python example, the entire cookie object is saved for future use instead of just saving the user token value. And again, this slide shows the JavaScript equivalent of a function that will query the API ML for a list of registered instances of the Ops MVS REST API. The response to this GET request will contain a JSON object containing this list in the response body. Now, this JSON list of services will be returned from this function to be processed by the main portion of our test application. Now, this slide shows how to call the Ops MVS REST API endpoint used to execute a REX program. The request body will contain a JSON object that specifies the fully qualified dataset name that contains the REX program you wish to execute, along with an argument string you wish to pass to this REX program. Now, in the context of this example, we're going to be calling a REX program to process the status data that we previously uploaded to the mainframe using the ZSS service. And the parameter to this REX program will be the fully qualified dataset name that contains this status information. Now, this function will return the JSON object sent back in the response body that contains details about the REX execution request, including the instance token assigned to that executed REX. And you can then call the OpsRex endpoint again that represents your REX instance in order to get the output that's actually produced by the REX program and the return code from the REX program once this REX program has finished executing. So again, now that we've got all these pieces together, we can call these functions in the order that I specified. So first, we're going to go ahead and call the login API to authenticate the user's credentials and get this authentication token. And again, it's sent back to us in the form of a cookie. And then next, we're going to go ahead and pass this authentication token into the routine that will query the API ML for the instances of the ZSS service, which again, remember, we're going to use the ZSS service provided by Zoe to upload our status document to a data set on the mainframe. And then what we're going to do is we're going to go ahead and use that same authentication token to query the API ML for the available instances of the Ops REST API. And again, both the URL for the ZSS service and the URL for the Ops MVS service will be stored in variables so we can use them in the future here. Okay, so using the URL for the ZSS service, we're going to now call a series of endpoints provided by ZSS to, again, create a new dataset member and populate this newly created member with the JSON object passed in as the SC data parameter to the populate dataset member function. Now that the event status information actually resides in a dataset on the mainframe, we can launch our REX program to process this status information. And again, we do this by using the URL for the Ops MVS REST API that was discovered on the previous slide. Now, this REST API provides, again, an endpoint to run a REX program on the mainframe that allows direct communication and interaction with the Ops MVS mainframe automation solution. Now, this API endpoint will use the same authentication token used by ZSS or really by any service that has registered with the API ML. So the launched REX program will receive the name of the newly created dataset member as a parameter and process any status data contained inside this member. The REX program can also communicate back to the caller by just issuing plain say statements as part of the REX language. And the user can use the Ops MVS REST API to query for any output produced by this REX program. And again, once the REXT program has finished processing the data, the newly created dataset member can then be deleted by calling another endpoint also provided by the ZSS server. Now, in the first example, I showed you how a single REST API service could be used to remotely perform an operation on the mainframe. Now, in this example, we kind of expanded the possibilities by using functionality from multiple REST API services in the same client program to perform an automation task. Now, the goal for these examples was to show how to increase functionality without significantly increasing the complexity or size of the client application. Now, we also decided to use two different programming languages to drive home the point that client applications based on calling REST API endpoints can run virtually anywhere and can be translated from one language to another. Okay, so now on the next series of slides, I'm going to show you some of the available tools that you can use to start writing client applications that call these REST API endpoints. Now, this slide shows a small list of HTTP clients that are available for a small list of client languages. Now, this list is not meant to be a recommendation. It's really only a starting point to help you in your research. Now, over the years, there have been quite a few client HTTP libraries written for the Java language. And the Java language itself includes two different libraries, the HTTP client library and the HTTPS URL connection library. Now, this HTTPS URL connection library is really not as developer friendly as HTTP client, but it's supported in older Java releases such as Java 8, which may be a factor. Now, there are other popular third-party Java libraries such as Apache's HTTP client and OK HTTP client by Square. So you should determine the requirements of your environment before choosing a particular library. The Ruby programming language also has a fair number of HTTP client packages, or what they call gems, and I've provided a couple of examples on this slide. Now, the net HTTP package is the built-in package to the Ruby language, and this tends to be the basis for other Ruby HTTP client libraries. The Faraday package is one such example, which actually builds upon the net HTTP package and provides additional benefits such as a simplified interface and automatic retry. Now, if you decide to use the Rust language, there are a lot of choices such as Hyper and Request. The Hyper package provides really low-level access if you need full control over the HTTP connection, while the Request package uses Hyper under the covers and again provides more of a high-level interface. Again, you should probably use some of these keywords when doing your own Google search to determine the best package to use based upon your programming language and platform. Now, if you need to interact with a REST API server from the mainframe platform itself, and you want to interact using a native application, you can take advantage of the IBM ZOS Client Web Enablement Toolkit. Now, this toolkit is available as part of the base z/OS operating system and contains tools needed to write a REST client application, such as a JSON parser and an HTTP protocol client. Now, these tools can be called from several native mainframe programming languages, including C or C++, COBOL, PL1, Assembler, and REXT. Now, this toolkit is supported when running programs as either a batch job or as a started procedure. Now, if you require TLS connectivity to the REST API server, you can use routines provided either directly by this toolkit, or you can use the system-wide AT-TLS policy to handle the encryption. Now, you can also use any other language or tool that is capable of running in OMVS. Now, some examples are JavaScript hosted by Node.js, Java, Perl, Python, and Go, just to name a couple. Now, IBM provides SDKs for several non-legacy languages, and you can really find these by using the search term, IBM Open Enterprise SDK 4, right? So now if you need a tool to help you test the ability to send a RESTful request to a REST API server, you can also download the curl for ZOS open source tool. Okay, so in today's presentation, we talked about how previously isolated automation solutions are being replaced by enterprise orchestration that attempts to perform automation at the business process level instead of the platform level. So in this new automation model, data and status sharing techniques should be common across the entire enterprise, which will allow new procedures in a business process to be easily incorporated into the existing automation strategy. So if these automation strategies are built on top of REST APIs, you can take advantage of the capabilities provided by this architecture. Now, these capabilities include scalability, high availability, request load balancing, reduced client configuration due to a single focal point, automated discovery of available services, and the freedom to choose the client tools best suited for the automation task. Okay, that is all I have. Are there any questions?
Thank you very much for that. It's very interesting, and I've personally played around with the CentOS Web Enablement Toolkit as well, so I've got experience using that. There's no questions in the chat, but what I will do is I'll open the floor, perhaps some final comments or questions if I can work out to do that. I'm going to unmute everybody if they want to ask you any questions. I think I've done that, but if I haven't,
it looks like they're all still muted.
You should be able to. You can unmute yourself. We don't actually unmute you. We just give you the ability to unmute.
I think I just ask all to unmute. So if I turn that should be. Is that how I do it? Anna, is that correct? So if anybody wants to come off mute, they should have that ability now, I think, is my understanding.
Yeah.
It doesn't seem like there's any questions coming, Phil. So once again, thank you very much for your time. I think
all right, you're quite welcome.
Wrapping up there. It's very interesting. Thank you. Oh, you've got some more information about the session feedback and stuff like that, yeah. And people can please complete the session code there and use the QR code to provide some feedback. But good. I don't think there's a registered charity this year, as you mentioned that earlier on, Anna, didn't you? But I don't think there is one.
Yeah.
No. Thank you. Thank you very much for your time, everybody. Thank you.